Okay. So let me start. Maybe some people will join a little later, but let's start now. So today we are very glad to have Nishant Mehta as an international speaker in our seminar, the IMC, Seminario IMC. He is physically in Chile. We are recording. Yes, we are recording. So he is physically in Chile, and unfortunately, we cannot have an in-person seminar because of the government shackling him due to a last-minute issue. But we still have the pleasure of hearing his talk, and hopefully, he will be free from these shackles very soon as well. Anyway, we are very glad to have him. Because this is a virtual seminar, so I ask everyone, if you want to ask a question, please do interrupt, because sometimes in the chat we cannot see the question. So do interrupt the speaker if you have a question and it comes to your mind. We will also have a space for questions at the very end. If you have more elaborate questions, we can ask them at the very end as well. So you can wait for that as well. Or if you need some clarification, you can just interrupt and ask Nishant in the middle. But please do so by removing your unmute yourself and ask the question. Nishant is currently an assistant professor at University of Victoria. And prior to that, he was a postdoctoral researcher at Centrum Wiskunde en Informatica. Is that in Netherlands, Nishant?
Yes.
So that's in the Netherlands, and also a postdoc in Australia, in Australian National University. And he obtained his PhD from Georgia Tech in 2013. So Nishant works mostly in the area of machine learning. And I understand that the focus is on online learning, right? Online learning and sequential prediction, right?
Yes.
Okay.
Yeah, that's right.
So let's give a virtual applause, and I'll let Nishant take over from here.
Cool. Thanks for the introduction, Federico. Yeah, so yeah, hopefully within a few days I'll be able to escape, but I'm following the rules, so it's good to do that when you're a visitor. So, so I would like to just say a little bit before I begin the talk. I know that not everyone in the audience is an expert in like online learning or necessarily does even machine learning. Also, group fairness or topics of the considering the societal implications of machine learning, decision-making systems. This is something which is important, but it's relatively new. So I hope to introduce both of these things here, okay, in some sense. So the talk, it's, if you've heard of, what people do in the theory world of machine learning, we usually prove upper bounds on the performance of an algorithm, like the loss. This talk is kind of the opposite. We're going to show that no matter how nice some adversary is in devising data, the algorithm will never do. It'll have a lower bound on the error that it can achieve, and that's useful in a certain fairness application. Okay. Now this is joint work with Cristobal, who's here, and my PhD student Ali Mortazavi, who's in Victoria, or will be soon. So I won't be covering everything in this outline. I might skip maybe the last part. We'll see how it goes. Feel free to ask questions throughout the talk, and I'll adapt as we go. So I'm going to start kind of easy with, I want to give you this model kind of example. So imagine, some very far away place in a distant future where, there's a researcher, maybe there's machine learning, and they post something on Twitter. And they posted something which someone didn't like, and then they're removed from Twitter. They're banned, okay? So, but the world is a fair world. It's a just world. So there is an automated judge. It's an algorithm. And the judge is going to do the following. The judge would like to see, should the person be let back into Twitter? And the judge is going to do the following prediction. So the judge will say, well, if I let the person onto Twitter, would they re-offend? would they again post something which maybe Twitter doesn't like? Okay. And if the prediction is negative, if the prediction is that they would not reoffend, then this judge, the algorithm, is going to let the person onto Twitter, right? So there's a consequence for the prediction. It affects this person. Okay. And if the judge predicts that they will reoffend, that this is the analog of committing a crime, it's something more serious, right? Then they will not be let onto Twitter. So the things I want to note here are, one, depending on the kind of mistake, the person might suffer some harm, okay? So there are two kinds of mistakes that could happen here, right? So let's say the person has a true label. The true label is 0 if the person would not reoffend. Let's say if they're good, okay? The true label is 1 if they would reoffend. Now, if you have a person whose true label is 0, so they're a good person, and the judge predicts that they would reoffend, this is what we call a false positive, right? You falsely predict positive. And this is the kind of mistake which harms the individual, right? And so this is the kind of backdrop for this, that decisions have implications and different kinds of mistakes might be harmful for the individual. The other kind of mistake, if you have a person who is bad and the judge predicts that they're good, the person is fine with that. They're going to be let onto Twitter, okay? It might hurt them in the long run, we don't know. Okay, so in terms of the online learning problem, we're going to say in every round, a judge is given some numerical descriptors about the person, okay? And I'll give an example in a second. And they're going to predict whether or not this person would reoffend. Okay. Now, to tie this to fairness, I want to consider the following situation where, in society, we sometimes have different groups of people that are like recognized, okay? And we might want to make sure that the amount of harm, predictions of false positives among the two groups is roughly equal. Ideally, we don't want any harm at all, okay? But we're going to have false positives in these prediction problems. And so maybe we have two groups. One of them in the machine learning community, we sometimes call them the elbow grease. They implement deep learning, algorithms. They run lots of experiments, okay? And then the rigor police prove the theorems, right? They're very rigorous, right? They use the whiteboard, okay? So these are two possible groups. And the judge might want to make sure that, after playing this game for 10,000 rounds, where in every round, an individual from one of the groups was present, they want to make sure that, the false positive rate is equal across the groups, approximately, okay? So among those people from group A, the fraction of rounds where we had false positives for group A is roughly equal to the fraction for group B. And the larger the number of rounds, the closer we want these proportions to be, right? So this is the setup, okay? So let me give you now a first concrete online learning setting, okay? So this is called agnostic online learning. Basically, we're doing classification in an online or sequential way. So in every round, right? So we're going to have a total number of rounds, capital T, may not necessarily be known by the algorithm, how many rounds there are. So nature, which you can think of as the one that generates the data, it could be adversarial. It could be like player number 2. So nature plays an example XT. The example can contain some features. For example, how many publications did this person have in some conference last year? And how many reviews did they do in the last 4 years? Okay, these kinds of things. And then the learning algorithm is going to predict a label, and it doesn't have to predict either 0 or 1. It could randomize. And so I'm going to say that it plays a distribution over 0, 1, right? If it plays 0.8, then with probability 0.8, it predicts the positive class. And nature, knowing everything that happened so far and possibly reacting to PT, it's going to choose the label YT, right? So it's going to be very adversarial, right? Nature knows the PT that was played, and it can choose the true label YT, which is either 0 or 1. And then we have a way of charging for the error, right? So the learning algorithm, it's going to pay according to the absolute loss. So the difference between the binary label YT and its probabilistic prediction PT, right? So if YT is 1 and PT is 1, then you pay 0, right? And so this is just some notion of error. And so in this problem, what we typically do in online learning is we don't necessarily just try to ensure that the cumulative loss, which is the first summation in the regret, is small. because nature is adversarial, and it might, in general, not be possible for the cumulative loss to be small at all. So instead, what we do is we compare the cumulative loss of the learning algorithm, which is the first summation, to the best cumulative loss, which is achieved by some reference class of rules, okay? So you can think of everything in this set, calligraphic F, under the minimum. Every one of those rules is going to be some classifier, okay? And given some input data xt, f of xt will give you a prediction. And so what the learning algorithm is going to do is it'll say, at the end of the game, let me look at which of these rules have the lowest cumulative loss. And then I'm going to compare my performance to the best of these rules in hindsight. And if one of those best rules is much better than the learning algorithm's performance, then the learning algorithm feels some sadness or regret, right? So this is the formal term that we use. And what kind of guarantee would one want to have here? So it turns out that the kinds of guarantees that we want on this regret, which is a summation of these quantities over t rounds, we want the regret to satisfy a property that we call no regret, which means that on average, when you divide by the number of rounds, the regret goes to 0, right? And we want it to hold in the worst case. So no matter what sequence of XT-YT pairs nature plays, right? We would like there to be a learning algorithm such that no matter what sequence nature plays, that the regret on average goes to 0, which put another way means that the cumulative regret that we have here should be sublinear in the number of rounds, right? So the way to think of no regret is basically, if no matter how long you play the game, if the regret is linearly increasing, right, then in some sense, the learning algorithm is not learning anything, right? If you play it for 100 rounds, it gets a certain amount of error. If you double that, the error doubles. You would hope that over time, the learning algorithm is figuring out which of these hypotheses, little f, is the best one. And then it starts, getting performance which is close to the best one. And then this discrepancy should not grow linearly, right? So this is, basically a first online learning setting. And this is the performance metric that we're going to be using throughout this talk. So let me now connect back to our example, right? And this is something which is going beyond the classic setting. So in addition, suppose that in every round, when nature plays an example, it also selects a group, right? So you can have group 0 or group 1, okay? And we can still strive to have an algorithm which has regret, which is sublinear, but now we also want to consider fairness, okay? And so how did I consider fairness before? Well, I framed it as you look, let's say at the very end of the game, for example, you look at each of the groups and we hope that their false positive rates are approximately equal, okay? An even stronger thing would be no matter what round you stop the game in, okay? Maybe you only play the first half of the game. So only at the end of the first half of the game, you might want the false positive rate between the groups to be roughly equal, right? And this was what we call any time, right? At any particular stopping time, we'd want the false positive rate to be equal. Let me say one thing in case it's confusing. If you're confused by the notion of the false positive rate, because the learning algorithm is playing a distribution PT, the way to think about it is that instead, suppose the learning algorithm in each round actually played a label, then the false positive rate is well-defined. And when it plays a distribution, it is randomizing, right? And so we can take an expectation to figure out what is the false positive rate, right? So, okay. And again, please interrupt, especially early on if you have questions, because it's important to get the setting.
Nishant?
Yes?
Yeah, just about the previous slide. So when we're talking about groups, I guess we will be concerned about this notion of regret you're writing down there, but over each of the groups, right? So there would be like a index G that you'll be looking at the cumulative regret on each of the groups separately.
I'm actually looking only at the cumulative regret overall, but this is a good question. So I think one could instead strive for the regret for each group separately to be low, but I'm actually looking at the regret overall. This turns out for the positive results later, this won't matter. Like they're going to be on the regret for each group separately. But yeah, right now it really is just like a single regret.
But there is an index G sub T, right? Because the group is G sub T and the index is T, right? Isn't it?
Yes, yeah. But that, okay. So the index, yeah, the index GT is only going to appear, it's only going to appear with respect to the constraints. So the false positive rate. So can you give an example of this F, this family F and the little Fs, just to get a... oh yeah, sure. Yeah, so to make it easy, let's suppose that the Fs are classifiers. They're not probabilistic in any way. So maybe you have data in a d-dimensional space, and every F could correspond to some hyperplane, which cuts through the space. And everything on one side is classified as positive, and everything on the other side is negative. To make it even simpler, maybe you only have one feature, which is a credit score. And every one of these little Fs might just be a different choice of a threshold, where everybody above the threshold is recommended for a loan, and everybody below the threshold is not recommended. Yeah. And for the purpose of this talk, well, at least right now, we're going to imagine this calligraphy F is a finite set, but this will change later on, right? So just to crystallize the problem, right? So we'd like to minimize the regret. And because we would like to enforce that the learning algorithm must have a similar false positive rate across both of the groups, right? So consider the rounds where we had group A and the rounds where we had group B. And compute the false positive rate for both of these sets of rounds, right? Because the learning algorithm, we will want it to satisfy this constraint. It's only fair that the rules that we are comparing to in this comparator class should also satisfy the constraints, right? Otherwise, we're comparing against rules. Sorry, we're comparing against hypotheses, little f, that do not play by the same rules that we're forcing the learning algorithm to play by, right? So that's why I say, let's also assume that these hypotheses are group fair. And when I say group fair, I mean exactly this blue condition over here, right? So this is a lot of setup for a problem which it turns out is not possible to get any positive results. So let me mention that. There was a paper in NeurIPS 2018, I think, by Avram Blum and Sakar Lucaris and Cerebro. And what they did is they showed that if you would like to have an algorithm whose regret grows sublinearly, and moreover, you would like to equalize these false positive rates. And by the way, they only require that at the very end of the game, that the false positive rate is equal. In the middle of the game, they could be wildly different, right? So it's a weaker consideration. Then it turns out that this is impossible. So the adversary has a strategy which ensures that any algorithm which makes the false positive rates across groups approximately equal at the end of the game can be forced to have a regret which grows linearly, which in the language of like machine learning is a useless guarantee. Like you're not able to get any useful bounds on the regret, right? So this is bad. So let me roll back and say what is possible. And the first thing I'm going to do is explain their strategy. And then we're going to get to new results, which are an upgrade of their strategy. Okay. So unfortunately, the issue is this balancing of false positives is something that is causing the trouble. So what they do in their work is they change the definition of fairness, right? And one should be careful when doing this. One should consider the particular application to see whether it's a good idea. And what they do is they don't just consider false positives, but they consider all mistakes. Okay, so whether it's a false positive or a false negative, across both of the groups, we strive to make the frequency of mistakes equal. Okay, so this is simpler, but depending on the application, right? This may not be a good idea necessarily, right? Because remember the example, somebody who would somebody who would post very offensive things on Twitter, if they are labeled as negative, then they're not very sad at all. They're pretty happy that they're being let on, right? But there could be other applications where maybe giving somebody a loan when they would very likely not repay the loan, it could be harmful to them because it can harm them in the future, right? It can mess up their credit score in the future, for example. So what we're going to do is we're going to use this mistakes-based definition of fairness, so equalizing the frequency of mistakes across the groups. And just because this is what they do, right, we're going to restrict the group fairness to be only at the end of the game. So you don't have to check, at every single round, do the groups have similar performance, but only at the end. And if you consider the setup, then it turns out that under this constraints of group fairness, you can get a good bound on the regret. And so I'm going to outline how they achieve this. And because now we're only considering mistakes, right, I'm going to abstract to a simpler problem. And in the simpler problem, right, this is the second online learning setting that I'm introducing you to in case you haven't seen these things before. So the way this problem works is we don't have any input feature vector at all. There's no XC, okay? So in every round, nature is going to play a group identity, just like before, GT. GT is, in general, it could belong to some finite set. Here it'll be either 0 or 1. And then the learning algorithm is going to play a distribution over a class of experts, right? So you imagine that you're investing in the stock market, and every day you have $100, and you're going to divide your $100 across D different experts that are going to, they're not even going to tell you, they will not tell you how they're investing your money, but at the end of the day, you'll figure out how much they lost, or won. A negative loss will be a reward, okay? So the learning algorithm is going to play a distribution, a probability distribution over the D experts, right? So in the case of 3 experts, it would be a point in the simplex like this. And then nature is going to decide the loss of every expert. So this LT is a D-dimensional loss vector. Okay, generally we'll assume that all the components are between 0 and 1 to make it nice. As long as they're bounded, it should be fine. And then the learning algorithm, right, is going to suffer the inner product of the probability vector PT with LT. You can think of this as the learning algorithm's expected loss when it selects expert J with probability PT comma J, right? And so this is the setup, right? Because we're only looking at mistakes now, so we don't care whether they're false positives or false negatives. So we only care about the loss of the learning algorithm, right? And so in this setup, let me mention to you one of the fundamental algorithms, right, which is known to get regret, which is sublinear, okay? The strategy is called Hedge, and it's a very simple rule. So what does the algorithm have to do in every round? It needs to choose a probability vector over D experts. So what it does is the algorithm looks at the past, and it looks at the cumulative loss of a given expert J over the first T minus 1 rounds. And the larger that is, the smaller the weight. And in particular, it's going to use this exponential updating strategy, right? So the exponential of negative eta you can think of as step size or a learning rate, okay? I'll mention what it is later. And then times the cumulative loss of the expert in the past. And so every one of these experts is going to be given this probability, and then you normalize by dividing by the sum, okay? So this is the strategy, right? So an expert that has much higher cumulative loss than some other expert is going to be assigned very low probability, right? So it's a kind of, you can think of that as a sort of like a soft max, or rather maybe like a soft min, right? So another strategy you could use is whichever expert was the best so far gets all of the probability, and everyone else gets 0. And this is like a smooth approximation of that, okay? So the guarantee that Hedge gives is the following. So the regret in this case, right, the cumulative loss of the learning algorithm, which is the first term in the summation, minus the cumulative loss of the best expert at the end of the game, is upper bounded by something which grows at the rate of square root of T. So definitely sublinear. And it has a very weak dependence on the number of experts as the log of the number of experts. Right. So this is good, but I've kind of disconnected from fairness because it turns out that the strategy that is used by the people that develop this result I'm going to show, what it does is it looks at the rounds that belong to, let's say, group A or group 0, and it looks at the rounds that belong to group B or group 1. And what it does is a strategy that I call interleaved hedge. So in any round, which is blue, that's group A, it's going to feed the data to one copy of the hedge algorithm. And for any round that belongs to the other group, it's going to feed it to a different copy of the algorithm, right? So you just have in mind running parallel copies of the same algorithm, and each copy is receiving disjoint data, right? Right. So this is the idea of the algorithm, and I'm going to sketch for you how the algorithm is able to maintain the fairness guarantee, and also why its regret is low. Okay. So the first thing is to remember, if we're going to require the algorithm to have a sort of approximately equal losses across the two groups, then we're also going to require the experts to have the same requirement, right? Otherwise, we're comparing it against a class of rules that are less restricted than the learning algorithm is, and that could be impossible. And so the first thing is, because the experts are group fair, right? What this means is that for any given expert, if you look at the error rate for the expert, oh, actually, I can't see something important because my screen's set up. Let me fix one thing. Okay, I think this is going to be better. Okay. So looking at the bottom, this E star B, what I mean by that is this is the error rate for the best expert for group B. And the thing on the right is whichever expert obtained that error rate, let's call it J star B. This is its error rate on group A. Okay, so both of the points I have here, they correspond to the same expert, but for different groups. And because of the assumption that the experts satisfy the group fairness constraint, we know that these two error rates must be close. So alpha looks large in the figure. It's meant to be a very small number, okay? And another thing that we know is that the best performance on group A can only be smaller than whatever the error rate that this J star B achieves on group A. And so now we know that from the first condition here, that E star B and E star A, right? The best performance on group A and the best performance on group B must be close, at most alpha. And then this is where we get into the kind of more interesting part. So for Hedge, we know that we have worst case upper bounds on the regret. So this E hat A corresponds to the copy of Hedge running on the rounds for group A. And we're looking at its average over all the rounds, its average loss. And we know that E hat A is going to live in this blue highlighted region here. And it's going to be at most epsilon greater than E star A, which is the cumulative loss of the best expert for group A. Okay, but we also know, and this is something which it's kind of sort of from the previous work, but it's actually an improvement on what they do. We can also show that using this Hedge algorithm with the learning rate, which is constant, that E hat A is never going to be smaller than E star A, meaning that it's trapped within this epsilon band. And the same thing is true for the learning algorithm's performance on group B, right? It's going to fit within this epsilon band, starting at E star B and going up to epsilon. And what this means is that at the end of the day, the learning algorithm's performance on groups A and B, right, which lies in this, this red set and the blue set, these must be close. They can be at most epsilon, which is going to be decreasing at the rate of 1 over square root of t, and plus alpha. And alpha is also going to be small by the assumption of group fairness. That's what the group fairness means. And so this is basically everything, because we're going to have low regret on each of the groups separately. And that implies we'll have low regret when you consider all the rounds together as well, it turns out. Okay. And so the key idea here that makes this work is this notion of the thing that was new is this notion of a best case lower bound. Okay. So let me refer to the picture again. So the fact that if you just look at the blue shaded region, okay, it turns out there's a result that says no matter what sequence of loss vectors the adversary chooses, for this algorithm, the learning algorithm's performance is never going to, its cumulative loss will never be smaller than E star A, meaning that its cumulative loss is going to be lower bounded by E star A. And this also corresponds to a lower bound on the regret, which is 0, right? So this is the key thing that was used in this the previous slide. And it turns out that when you have a constant learning rate, then in many examples, you can get that in the best case, like no matter what the adversary does, the regret is always going to be non-negative, right? You could imagine a different situation where a learning algorithm, if it's comparing against a small set of rules, and if it carefully decides in which round to use which rule, maybe it could actually do better than the best rule within this class. And then the regret would be negative, right? Its cumulative loss would be smaller than the best rule in this class, right? But here we're saying that basically this cannot happen for this algorithm, that the regret is always going to be non-negative. Okay. But so this result is pretty much like, this is a previous result from previous work, but this is kind of the beginning of our work. So what they were doing in this previous work is they were only looking at the fairness constraints at the very end of the game. Okay, meaning that if you have this example over here, well, at the very end of the game, each of the groups has had the same cumulative loss, right? So the fairness constraint would be satisfied. But if you look at the middle of the game, this is certainly not the case. In the middle of the game, the learner has only had losses on group A, and it's had no losses on group B, right? So what we would like is to have an anytime guarantee, right? We would like the losses to be balanced approximately, no matter when we stop the game, right? And so that's what we would like to do. And so to do this, it turns out that we can't use this strategy hedge with the constant learning rate from before, because hedge with the constant learning rate, it has a regret upper bound at the end of the game, but it does not have what's called an anytime upper bound. If you check the performance of the algorithm in the middle of the game, it may not necessarily have a good upper bound on the regret. That there is an algorithm, right? And if you're familiar with like optimization, this schedule for A to T might seem familiar to you, right? Or also doing I guess stochastic regime descent. There's another version of this algorithm called decreasing hedge, where we use the same strategy from before, but the learning rate is decreasing over time at the rate of 1 divided by square root of t. And when you use this anytime strategy, which doesn't need to know the number of rounds ahead of time, then it turns out that for every round, it will have a regret bound that is satisfied, right? And it'll be essentially the same regret bound that I showed before. However many number of rounds you've run so far, it'll be growing as the square root of that number of rounds times the log of the number of experts. So this is old news. This is not new. But what we want, in order for the argument from before to work, we also want a lower bound that holds no matter what nature does, right? So this is what I call, instead of a worst case upper bound, we want a best case lower bound. Okay, and it turns out that, you know, this question in red that I have here, we can answer it in the affirmative, and I'll show you a little bit about this in a second. We can show a regret lower bound, which the first thing to note is that there's a negative sign, okay? And the other thing to note is that the form of the lower bound is essentially the same as the form of the upper bound. So for decreasing hedge, the upper bound is the square root of t times log d. Yeah, that's actually like, there's no constants at all. In an upper bound one can show. And the lower bound is essentially the same, but with a minus sign and a factor of 1/2. Okay. And this, by the way, the lower bound is tight in the case when d is equal to 2, right? Meaning that like this rate is the correct rate when d is equal to 2. We know that for sure. So one thing that one could ask is, you know, can we get this best case lower bound? The answer is yes. But more generally, right, stepping back and, you know, thinking a bit more generally in terms of theory, you can ask, okay, well, decreasing hedge is just one algorithm out of many, many, many choices of online learning algorithms. Is there some general framework of algorithms we can consider? And within that framework, this big ball of algorithms, is there some subclass of algorithms for which we can prove that no matter, right, what nature does, the algorithm is never going to outperform the best expert by that much, right? Put another way, can we show a non-trivial best case lower bound, saying the algorithm will not perform too good, right? And so just to complete the story from the fairness part of the talk, because we are able to show this best case lower bound for this, this interleads version of decreasing hedge, at the end of the day, we're able to get what we want. We can show the regret bound at the bottom. That part is kind of easy. But also because we have this best case lower bound, which it has this rate of negative square root of t log d. If you go back to this figure over here, every one of these red regions, if you imagine extending it a little bit to the left by an amount which is like square root of t log d, okay? Well, the red and the blue region is still going to be, they're still going to be close, right? We've only increased their distance by at most square root of t. And because I'm looking at a rate over here, I further divide by t. So even if the blue and the red regions extend more to the left, we still know that every point in the blue region is going to be close to every point in the red region, right? So this is basically what's going on. We can get a best case lower bound, and we can still show that no matter what round we stop the game in, the error rates across the groups are going to be close. And if you only play the game for 5 rounds, then you're not going to get a very good guarantee. But if you have a larger number of rounds, right, then the error rates are going to decrease at the rate of square root of t at least. Okay. So I'm gonna switch now. I want to talk more generally about best case lower bounds, right? So I'm going to get away from the fairness story. So if you didn't follow some parts of it, we're going to reset in some sense. So that's fine. Okay. So I want to show one really cute result first. This is, we're going to do the following thing. So imagine you're playing a game against somebody and you're wondering, in the worst case, against the worst opponent, right? What is the error that you're going to suffer? Now, there are different things that you can do. One thing that you can do is you can try to work out for your algorithm, what is the worst case opponent exactly? What are the moves that they're going to make? And when they make those moves, you can compute, hopefully on paper, you can compute what your loss is going to be against the worst case sequence, right? And this has been done before in online learning. What we're going to do is the opposite. We're going to compute the sequence for which the regret is minimized, for which it's going to be the smallest. And we're going to do that for this algorithm, which is called decreasing hedge. And because it's kind of complicated to do, we're going to restrict to the setting where there's only 2 experts. And every expert is going to get a loss in each round, which is either 0 or 1. So we have binary losses. Okay, so a play out of the game, the adversary is going to play this blue sequence, for example, where in every round there's a loss vector, which has binary losses. And there's only 2 components because there's 2 experts. And I won't, there's a few rules that we use that show that we can iteratively convert any sequence, any arbitrary sequence like the one above, into what I call the canonical best case sequence, which is the sequence below, which has a lot of 0 1s. And then it's kind of strange. It has 2 0 vectors. And then it has a lot of 1 zeros. And we can convert the blue sequence to the red one step by step. And every step of the way, we will never increase the regret of the algorithm. What that means is that the sequence in red, provided that I think the number of rounds needs to be at least 16, and we're going to make it even, okay? Then it turns out that the sequence in red is the sequence such that this algorithm gets the lowest value for the regret. And so once you have that sequence, sorry, I'll skip these because of time, but these are like the steps that we use to convert the sequence. It's super interesting, but for time, I should not cover it. Once you have that particular sequence, which is here on the right side of the equality, then you can analytically work out what is the regret of this particular algorithm on that sequence. And it turns out to be negative order, big theta, square root of t. Okay. And something which is open, which I probably think is not that hard, would be to scale up this example for the case of D experts. And we just want to show that there exists a particular sequence with D experts where the algorithm gets regret, which is negative square root of t log d, because this would show that the previous bound that I showed is tight, that it can be achieved. Okay. So let me step back a little bit. Now we're gonna, I want to kind of say a little bit more about some background in online learning, and then show you a more general lower bound for a general class of online learning prediction algorithms. So if you're familiar with convex optimization, but not familiar with the online version, then this might be interesting for you. So there's a setting called online convex optimization. It's like convex optimization, but in every round, an adversary is going to be selecting a convex cost or loss function, okay? And the learning algorithm is going to be playing its actions from some compact convex set. Okay, and I'm going to ignore things like diameter and so forth. I just want to give the essence of the protocol. And so the way every round unfolds, it's similar to the online learning setup. So the learning algorithm is going to play an action, WT. Nature is going to play some loss function, FT, and then the learning algorithm will suffer the evaluation of that cost function on WT. And just as before, we can write out the regret. You notice now that this calligraphic W, right, the feasible set for the learning algorithm, it's a convex set. It's going to be an infinite set, right? It's going to have, right? So it's going to be a large set. Okay. So in this setting, there's a general class of algorithms that can be used in order to get low regret in this setting, and this is known as the follow the regularized leader, right? And with an additional thing, adaptively selected regularizers. But let me first give you the intuition of this update. Okay, so for the intuition, I'd like you to ignore the Greek the phi t of w at the end. Right. So suppose that I'm sitting at the beginning of round t+1, and I'm the learning algorithm, and I can do the following. I can look at whichever w minimizes the cumulative loss over the previous cost functions that I've seen. Right? So this is a greedy strategy, basically. I'm following the leader, where the leader is defined as that W, which had the minimum cumulative loss so far. Okay. This strategy turns out to be horrible in many situations, although it sounds intuitively like a good idea, right? Because an adversary can force the algorithm to some kind of bad switching behavior, where it's switching between W1 and, sorry, let's say some X and some Y in alternate rounds, and in every round the algorithm plays X is really bad, and every round algorithm plays Y is really bad, right? So the way to fix this is we stabilize, and the stabilization is done by the choice of a regularizer being added, this phi t of W, right? So it's some sort of penalty term. And so this is called follow the regularized leader for this reason. And without getting into a lot of details, in general, for many algorithms, the phi t, it's a function. It can depend on all of the cost functions that have been revealed so far. So it can be adaptively selected. And for those of you familiar with Adagrad, for example, it doesn't exactly fit into this framework, but the regularizer part does, right? Adagrad will use a regularizer, which depends on the past gradients that we've seen, i.e. information related to the functions that we've seen in the past. Okay. And so this general strategy, it's known to admit a regret bound of the following form, right? Where there's a term which involves the evaluation of the regularizer on the optimal point at the end of the game, W star. And then there is another component. And then the last one, which is what I want to focus on more, is something related to the gradients, okay? So something related to the size of the gradients as measured according to some norm, which can again be adaptively defined. Okay, but yeah. So let me connect with something that we've already seen before. So before we saw this decision theoretic online learning setting. In that setting, in every round of learning, the nature is going to play a loss vector, and the cost function is the inner product of what the learning algorithm plays W with the cost vector or loss vector LT. So this is a particular situation that we would call online linear optimization, because the cost function is a linear function of W, right? And so Hedge, which we saw before, it turns out to be the special case of online linear optimization, where the regularizer that we select is the it's a scaled version, scaled by 1 over eta of the negative entropy, right? So remember that W is going to be a probability vector. And so the summation J equals 1 through D, Wj log Wj, is simply the negation of the entropy. And one can work out that we get exactly the update rule over here, where Wt comma J is exactly what I showed you before, this exponentially updating strategy. Okay, and then what we saw before is that this thing, which I'm now going to view as a particular instance of follow the regularized leader, it has this regret bound where L hat T, the cumulative loss of the learning algorithm, is going to be at most bigger than L star T, the performance of the best expert in hindsight, by at most square root of T log D divided by 2. So this is something that we've seen before, right? But now it's kind of in a different, in this more general framework. And for decreasing hedge, we have something similar, but this bound will hold no matter what the value of capital T is, right? So the algorithm doesn't need to know how many rounds it's playing. A bound like this will be satisfied in every round. And as T gets larger, the bound increases, at the rate of square root of T. And I'm going to, in the interest of time, I'm going to skip the second thing, but basically, if you have a game where the best expert has very low cumulative loss at the end of the game, you can get much better guarantees. If the best expert's cumulative loss is close to 0, then you don't want to pay in your bound square root of T. You can pay something much smaller, which scales as the size of the best expert's cumulative loss. Okay, but these are all different kinds of adaptivity. So learning algorithms that adapt to the data in different ways. And just like a one-sentence summary for AdaGrad, or the adaptive gradient method, it also has a guarantee, and its regret bound, it depends heavily on geometric information related to the gradients that have been revealed, right? So just a high level, this little g and the big G, these are some simple functions that depend on the past gradients that have been revealed throughout the game. And if the little g's, the gradients that you've seen so far, are small, then we get a better regret bound. Okay. And I'll skip this as well because it's in the interest of time. I want to show you very briefly this general result. I don't know if I can even sketch for you what it is, but I'll show you some applications. So this general result, I'll mention one thing. So you've seen the regret before. In this regularized regret, if you ignore the phi t of W, then what I've written here is exactly the regret. Cumulative loss of the learning algorithm compared to the best expert in hindsight's cumulative loss. When you add this regularization term, phi tw, this is something that we call the regularized regret. It turns out to be very instrumental to showing the best case lower bound, right? Maybe I'll try. So in a few steps, we can show that the regret and the regularized regret are not going to be too different in the sense that the regret will be lower bounded by the regularized regret plus some additional term. Okay. And another key thing is that imagine that your regularizer is the negative entropy. Okay. And imagine that your learning rate is the one that we have for decreasing hedge. In that case, it turns out that the regularizer at a given point W in round T is always going to be no larger than the regularizer from the previous round. Okay, meaning that if this is true, then we can show that the regularized regret is only going to increase as time goes on. And this is useful because in just a few steps, we can show, let me just cut to the conclusion, we can get this theorem, okay? So for this general class of strategies, adaptive FTRL, which includes as a very special case, decreasing hedge, right? We can show that there's this best case lower bound where the regret is lower bounded by a couple of quantities involving the regularizer. And in an example, I'll show you what these will be. And also, what are these alpha t's? So remember before when I said, let's suppose that phi t of wt is upper bounded by phi t minus 1 wt, right? That the regularizer is like, it's not growing over time. Well, if that's not exactly true, then we'll add a slack variable alpha t. Okay, so in many situations, we'll be able to set alpha t to 0, right? Meaning that this regularizer is really, it's not growing over time. Or if it's growing, it's because it has a minus sign, right? So it's -5, and the next round it's -6, -7, and so forth. So let me give you an interpretation of this, okay? So this is like something that I think may be easier to understand. So suppose the regularizer does not change. So in every round, you do the exponential updating strategy using the entropy, and the learning rate is constant, okay? So the regularizer's functional form doesn't change, and the learning rate doesn't change. So phi t and phi 0 are the same. So these two infimum over here are going to cancel. And moreover, in this particular case, because the regularizer doesn't change, this phi t wt and phi t minus 1 wt, those are the same. So the alpha t's can be set to 0. And then we get this really beautiful thing, which is that the regret is going to be lower bounded by 0. This is saying when you play against an adversary, even if the adversary is going to try to help you, right, and be as nice as they can, your algorithm is never going to outperform the best expert, ever, right? So it's like a very kind of intriguing thing. Even if the adversary is trying to make your life easy, your regret will never be below 0, right? Not even like by some chance. This result was already known. And by the way, if you don't use a regularizer at all, if you use follow the leader, then the constant regularizer, it's always 0. And follow the leader also is never going to have regret, which is smaller than 0, meaning that it'll never outperform the best expert. Okay? And then to give one more example for decreasing hedge, in this situation, we have the negative entropy. And as the learning rate gets smaller and smaller, we're going to be scaling the regularizer by 1 divided by the learning rate. So as time goes on, the regularizer, it's a negative number, and its magnitude is getting bigger and bigger. So this is exactly the situation where these alpha t's again can be set to 0. But now we have to be careful about phi tw and phi 0w and the ints. And what we end up getting is this results at the very bottom right of the slide, which is this thing that I showed kind of midway through the talk, this best case lower bound for decreasing hedge. Okay. And finally, let me just mention, let me mention one more thing, because within within the online learning community, AdaGrad is a big deal. Within the deep learning community, it's a big deal, right? So it's nice to say something about an algorithm that people often use. And it turns out that the AdaGrad that we often use, it does not fit into the framework that I mentioned before, for the reason that if you look closely, right? So imagine in every round I have a cost function. What AdaGrad does is it doesn't consider the cumulative loss based on the cost functions you saw. It considers a first order approximation by using the gradients from the successive rounds. So it's basically running follow the regularized leader on a linearized version of the costs. So this we'll call linearized FTRL. And when you want to prove upper bounds, the linearization helps you because the regret for the original game can be upper bounded by the regret for the linearized version of the game. The inequality doesn't go the other way. And so for showing best case lower bounds, we kind of hit a wall with this version of AdaGrad. But fortunately, we have Cristobal, who worked out this really amazing thing, which is, well, okay, let me say, I think maybe he might say I'm overclaiming a little bit. So maybe this is something that kind of appeared in the literature, but there is more work, to do. So if you consider the, let's call it the pure version, adaptive gradient FTRL that actually runs on the cost functions. But if you look at the regularization term, it's still using this complicated dependency on the previous gradients. For this thing, you can show upper and lower bounds, which are remarkably similar. The lower bounds will have a negative sign, right? And this is, we don't know if the lower bounds are tight, if they can be achieved. But it's kind of interesting that we get something which is, there's this sort of symmetry, right? Where the, for the diagonal version of AdaGrad, which is used in practice, right? I'm focusing on the part of the upper bound in red. And that is exactly the same up to a scaling as the lower bound with a minus sign. The more expensive full matrix version of AdaGrad that involves this complicated, you have to do some complicated operations involving like, eigen decomposition, right? Again, we have this roughly like matching upper and lower bounds, right? So yeah, I think that's all I wanted to say. I'm really excited about the last part of the talk, but in the interest of time, I should skip it so we can leave time for some questions. So let me just summarize. So what have I talked about? So group fairness in the context of machine learning is important. There's also many other kinds of fairness as well, right? And if you like philosophy, then you're free to argue for your own things and try to make them mathematical. We're able to show that for this anytime notion of group fairness, which I claim is what we really want, that we can get a no-regret algorithm which satisfies this for decision theoretic online learning. That was the original motivation for this work. But then going more generally, if we do FTRL with these adaptive regularizers, then we can often prove these non-trivial best case lower bounds. And we don't know which one of them are tight, but at least the bounds that we proved, they seem to have the same order as the worst case upper bounds. Okay. And maybe I'll stop there because there's very little time. So yeah, please ask questions if you have any. Sorry for going long.
Yes, please. Thank you very much, Nishant. But yeah, for everyone else, please ask questions. We have a space for questions. Any questions? Everyone's very shy today, as usual in the virtual setting. There we go. Cristobal, go ahead.
Yeah. Hi.
Hey. Yeah. Thanks for the talk. So I have several questions actually, but I guess something it's intriguing is this difference between linearizing and non-linearizing, at least in the online convex setting, right?
Mm-hmm.
So
not sure if that's the best.
Of course, FTRL, it seems to be out of the game because just linearizing sort of messes up the lower bounds, and we can show that these are negative linear. You can get negative linear regret, but of course, in practice, people like to linearize things. The algorithms become much nicer. So, is there a hope that any sort of algorithm that doesn't involve what beyond FTRL we could prove a best case lower bound for? I guess that's the main.
Maybe one thing that would help partially build some intuition is if I could talk a little bit about the situations where we know life is hopeless. So there are examples where the linearized version can get regret, which is negative linear, which in plain language means that extremely outperforms the best expert, right? And this is this thing which I skipped, but I think there's a figure which even kind of expresses it. So the setting, the setting here, the thing I want to highlight is that we have some online convex optimization setting where the loss is strongly convex, right? And it turns out that because the loss is strongly convex, it was able to show that in this situation, when you run the algorithm in a particular example like this one, so imagine you're doing weather forecasting, and in the first half of the game, you have all zeros, and then the second half of the game, you have all ones. A very natural strategy that one could use, what it ends up doing is it quickly converges to the probability zero in just a few rounds. And the gradients eventually vanish because of the strong convexity. And so the algorithm effectively stops updating. It has very little memory. And because it has very little memory, at the beginning of the second half of the game, where the outcomes change to all ones, meaning it's going to be raining every day, the algorithm, having little memory, it can catch up quickly and it can switch to one. So basically, in this situation, if you want to predict the weather, and if half the days are rainy and half the days are sunny, in hindsight, the best thing you should do for the squared loss is predict 0.5. But this algorithm is actually predicting essentially zeros in the first half and ones in the second half. And so the one thing I can say is if you have a strongly convex loss, then I know examples where for this linearized FTRL, we would not be able to show any interesting best case lower bounds. But then that opens the door to, what if I don't have strong convexity? What if I have a loss which is almost linear? Maybe it's piecewise linear, right? Something like the absolute loss. That would be a candidate where like it would be nice if we could maybe still show something positive, right? To show still show a best case lower bound, which is like sublinear. But yeah, yeah. So I haven't looked at this yet, or we haven't looked at this yet. But yeah, was there another part to the question, or let's see?
No. You answered perfectly. I don't know if we have time for another question, but yeah, I guess the other one may be very brief, right? But there's this big assumption in the online, the group fairness setting, which is the fact that the predictors themselves are fair.
Yeah.
How one can even build those, predictors or experts rather.
Right. So this is another important thing. So like in practice, you wouldn't really know if some reference class of predictors are fair. And so, one thing that we wanted to do is in an online way, try to kick some of them out. So if they're witnessed to be unfair, then we might try to eliminate them, right? And this corresponds to a set of experts that you're comparing against, which can change over time. And in terms of being able to show positive things for our algorithm with respect to fairness, I think this is something that we're stuck on, like wasn't able to do anything. But let me give a different, maybe more positive answer. So one thing you could do is say, let's not assume that the class of experts is fair, but we're going to compare against a larger class. Okay, so the larger class would involve us being able to mix across experts. So if I have an expert here and an expert here, and in every round, the experts are playing some probabilities, then maybe I allow myself to also play everything in the convex whole, right? So in any given round, one particular expert would be a, let's say, 1/2 mixture of two of my original experts. And some of these mixtures, right? Maybe some of those are going to satisfy the fairness constraints. And I think this has been explored in another paper. I don't remember the title, but I think it's it's the paper by I think Bo Wagner is on it. I don't remember the title though. What was it? But just to include, so this idea of like a changing set of comparators, it's very difficult to deal with, and so far we didn't have any positive results for that. But I think it's a good open thing to work on.
Thanks.
Okay. If there are no other questions, I think you can still feel free to email Nishant, right? They should.
Yes. No, for sure. If you want pointers to literature, for sure, email me.
Okay. So thank you very much for the talk. I hope that you have a pleasant stay, and we will keep in touch. And Cristobal, you can also email Cristobal, right? Because it's just in case, right? Someone's interested. Okay. Thank you very much, Nishant, and I'll stop recording now and finish the meeting.
Muchas gracias. Thank you. And
okay. Thank you.
Thanks.